Hello class. So today we're going to go ahead and learn about is the mean value theorem of an integral. So let's pretend I got the same function. Let's call this function f. And we learned that if I wanted to do some sort of approximation to the area under this curve, I have two options. I can actually have the options of doing my trapezoidal, my rectangular, approximations by doing the Riemann sums. So if I want an under approximation, and let's go with just a trapezoidal, I'm gonna go ahead and see that this curve right here, in order for me to do approximation from A to B, let's go ahead and go with all of these are gonna be from A to B as my interval, from A to B, and let's pretend the red curve is a function f. So if I wanted to do an under approximation, that means I need to have less than the area. So it appears that I would do it here at my B value, and it looks I would draw a little rectangle like this, and this would be the area. And as we can see, there is some sort of area missing, like this part right here, right? There is some area. This is why it's an under approximation. If I wanted to do an over approximation, it appears that I would do it at where my value of a is intersected with the function here. So I would go ahead and draw my little rectangle like so, and we can see that I'm covering all this area, and all this area has over approximation because all of this area right here is part where the function does not exist. So this is over approximation. Just a quick little summary. So what we want to go ahead and recall is the mean value theorem. So we learned that in the derivatives, that if we were to have some sort of function, let's go ahead and make this something cubic, I guess. We have, let's see, something like that. The mean value theorem says, the mean value theorem says that I can go ahead and get an interval from A to B, that if I go ahead and draw the secant line, there is a value C right here that has that same point, that same average. So right here the graph is a little bit off, but there is a line right here that I would ideally have the same secant line as the function. Well, you're probably wondering, well, how does this work for MVT of an integral? Well, the same thing, we're gonna go ahead and find a value C. Let's go ahead and say it's right here from the interval from A to B, and then we're gonna go ahead and draw that same area. So we're gonna say that if I was to draw this little rectangle right here, I would have this area right here. And what the mean value theorem of a trapezoid says is that this area will be the same as the area of the other figure. But you're probably thinking, well, that's not true because look at this area left over. Well, this area left over, you're right, that is above, but according to mean value theorem, that area fits right here where I have this part right here. So that's what I'm trying to say, that there is a value C that works with this mean value theorem. So you're probably wondering, what does this mean? Well, pretty simple. There is an interval. We want to find this area right here. The interval is going to be from B minus A, right? This will be the interval. And how do we find the height at this point? Well, this is also called delta x, and this will be the height at that point, at C. Well, that's what we're going to go ahead and do. And to find the area of this rectangle, all we have to do is multiply f of C times my delta x. Okay? So you come up with these two functions. We're saying that the area under the curve is the same as the area of the rectangle. Isn't that so cool, guys? That's like super awesome. Now, depending how you see it, some people will go ahead and divide by b minus a, this coefficient. Then they appear with this same equation right here. So that is what the mean value theorem says. It says if you go ahead and find the integral from a to b, it is the same thing as the area under the rectangle I've given C. So let's go ahead and do the first example together. So I'm going to erase this real quick, and I'm going to go ahead and use this one right here. Okay, so let's go ahead and use this one on the top left, and it says if I integrate the function from A to B, I can get a value C that multiplies, that gives me the same area. So let's go find that C. Find the C value. So pretty straightforward. Let's go ahead and integrate from the -1 to 2 on the function 1 plus x squared dx, right? Because that's the variable we're working with. Not that bad. It looks like the integral of 1 is x. The integral of x squared is x cubed divided by 3, all over -1 to 2. Now we evaluate using the fundamental theorem of calculus that it says f of b minus f of a. It's going to give us the following. Well, let's go ahead and do that little work. Oops. And it will be, let's do it in green. I like green. So let's go ahead and say that f of b will be 2 minus 2 cubed over 3. That is my f of b part. And I'll do my next part in sure pink. Subtract it minus my f of a, which is my value here. So it's going to be -1 plus -1, whoa, -1, is that high navigation? Sure. Whoa, something happened, guys. Plus my -1 cubed over 3. All I did was substitute it here. So we can simplify this. Sure, orange works. 2 minus 2 to the cubed is 8 over 3. Subtract it from -1. -1 to the third is still -1 over 3. This -1, negative sign distributes to both parts, and it gives us the following. 2 minus 8 thirds plus 1 plus 1/3. So far so good. We have like terms. That this 2 and this 1 give me 3. Subtract it from this. Looks like something's funny here. This -3 8/3 plus 1/3 gives me 7/3, and I think there's an error around here. Let me pause real quick. Let's see. Is if I subtract this, we are some silly gooses. There you go. Do you see this little negative that I carried through the entire part? That is supposed to be a plus. Guys, why didn't you tell me? That makes this a plus, that makes this a plus, that makes this a plus. Oh my goodness. That makes this a plus. I'm so sorry about that. Why didn't you tell me? Okay, so we got 2 plus the 1 gave me the 3, so right here. Then 8/3 plus 1/3 gives me 9/3. There we go, that looks better. This gives me 3, 9 divided by 3, that is 3, that gives me 6. 6 is the area under the curve. Pretty cool. So if we were to draw this is right here, this is 1, and this is x squared, like this, and then 2, and it gives me 1, 2, 3, 4, so something like that, and it just reflects over. So we're saying that this graph from -1 to 2 has an area of 6. All of this pink stuff is an area of 6. 6. Okay, now I'm going to erase this work to go ahead and find the C value. So, bye, pretty work. I will miss you. So we're saying that all this good stuff is equal to 6 units, right? Because that's what the integral says. Now, because that's the best I can do, fellas. Okay, that's the best I can do. Okay, so it's saying that all this, it has an area of 6. So 6 is equal to, 6 is equal to f of c b minus a. Well, let's substitute. 6 is equal to all this good stuff that I'll put in red. F of c, b, remember this is a, this is b, 2 minus a minus 1. So we got 6 equals f of c. 2 minus minus 1, that's 3. So according to this, we divide by 3, divide by 3. 2 is equal to f of c. Now you might be wondering, what is f of c? Well, don't worry, f of c is actually c substituted into the function, and we know the function f of x is equal to 1 plus x squared. So all we're going to go ahead and do, let me go ahead and substitute here. 2 is equal to, instead of writing my x's, I'm going to write this c right here. So it's going to be 1 plus c squared. Easy peasy, easy quadratic equation. So it's going to be this value right here, we're going to say is minus 1, right? We're solving for c. So we got 1, what's going on? 1 is equal to c squared. So c is the square root of 1. Sorry, c is equal to the square root of 1, so that's plus minus 1 equals c. Okay. So now, ask yourself, c is equal to 1 or negative 1. That will have the same area as a rectangle. I'm sorry, as the area under the curve. Well, I can't write. Okay, so negative 1, is it on the interval? Is negative 1 in the interval that we just found? Negative 1 to 2. Well, if I made a rectangle right here at negative 1, there's no height because, so there's no width because it starts at negative 1 and it ends at negative. So you should probably think that this negative 1 does not work for us, right? That negative 1 does not work because if I was to make a little rectangle right on the line, there would be no width. But if I was to make a rectangle right on 1, right, my other option, right at 1, which is right here, and I make this little rectangle like so, according to this theorem, I can go ahead and see that this will be the same area, because whatever area is missing right here has already been accounted for because there is an area missing. So what we want to know is that this area right here is the same as that area there. Isn't that cool? The value c is telling us that, hey, at c equals 1 right here, right? At c equals 1, we can draw a rectangle that meets the function to create this beautiful, beautiful rectangle. That's pretty cool, guys. Because that area would just go bloop right here. That is the mean value there. Thank you.